Hello students, and welcome to our chemistry lesson. So this is a continuation of the oxidation number. So in our previous lesson we saw that we have basically two uses of the oxidation number. We saw that by use of the oxidation number we can be able to name inorganic substances, and also we can be able to track the movement of the electrons in the redox reactions. So this is just a recap, just one more example. We're going to calculate the oxidation number of nitrogen in the following compounds. So our first compound here is N2. So N2, this is a gas, this is a molecule. So what did we say in our rules of assigning the oxidation number? If a compound is a molecule, then the oxidation number is always 0. So nitrogen gas, the oxidation number of that is 0. It has it's 0. Next, we have this one, NO. So what is the oxidation number of NO? So we say let the oxidation number of nitrogen in this compound be X. So X, and of course we know the oxidation number of oxygen is always -2, apart from the exemptions that we talked about. So for this one, oxygen has an oxidation number of -2. So if we add that, it should give us the overall charge of that compound. But because this is a neutral compound, the charge is 0. Then the sum of the oxidation number of the two atoms here should add up to 0. So X plus -2 is equals to 0, so X is equals to 2. So that's why we say this is nitrogen 2 oxide. So the oxidation number of that one therefore is +2. Remember we said when writing the oxidation number, we start by the sign followed by the number. That one, we're going to look at N2O. So as usual, let the oxidation number of nitrogen be X. But how many nitrogen do we have here? We have 2, so it should be 2X. Oxygen has an oxidation number of -2. This is also a neutral compound, so the sum of the oxidation number of the two elements should give us 0. There we go. So here we have 2X plus minus is equals to -2, should give us 0. So 2X is equals to 2. So X is equals to 1. This explains why we normally say this is nitrogen 1 oxide. So the oxidation number of nitrogen 1 oxide is +1. Let's go to the other one. The other compound is NO2. So as usual, so we have X plus we have 2 oxygen, and each oxygen has an oxidation number of -2, should give us 0. So X plus, that's -4, should give us 0. Take -4 to the other side and we are left with X is equals to 4. Nitrogen 4 oxide. So NO2 oxidation number is +4. Finally, the last one in our example here is NO3, and it has a charge here. This is a radical, this is nitrate. So what is the oxidation number of nitrogen in this radical? As usual, let the oxidation number of nitrogen be X. Oxygen in this case has an oxidation number of -2. But how many oxygen do we have here? We have 3. And because this is a radical, so the sum of the oxidation number of nitrogen and oxygen should give us -1. So here we have -1. So here we have X plus -6 is equals to -1. X is equals to, this one goes to the other side, have -1 plus 6, and X is equals to 5. So the oxidation number of nitrogen in this compound is plus 5. So next we're going to follow some examples. We're going to track the movement of electrons in redox reaction. So next, in our next exercise, we're going to track the movement of electrons in a redox reactions. With me here, I have an equation whereby I'm reacting ion 2 sulfate with hydrogen peroxide and sulfuric acid to give us ion 3 sulfate plus some water. So this is a redox reaction, and we're going to use the oxidation number to identify the species that have been oxidized and those that have been reduced. So we are going to write the oxidation of each compound, but before that, it is important to make it more easier. It's always important to use an ionic equation if possible. If we check at this ion, in this case, this is ion 2. The oxidation state number of ion here is 2. Sulfate should be -2. I've treated it as a radical. Then water here, hydrogen has an oxidation number of +1. Oxygen, now this is one of the exemption, it has an oxidation number of -1. Hydrogen in the acid here has an oxidation number of +1. Sulfate has an oxidation number of -2. In this case, now this is ion 3, so the oxidation number of ion here is +3. Sulfate, as usual, should be -2. Hydrogen in the water, the oxidation number is +1, and oxygen, the oxidation number of oxygen in water is -2. If you're very keen, you should note that the sulfate is remaining the same. The sulfate is remaining the same. Here we have the sulfate, and from the acid, it's just remaining the same. So if we were to write the ionic equation, then we would omit it. Let's start with the first one. What is happening to ion? The oxidation number of ion was +2, but after the reaction, it changed to +3. So ion oxidation number changed from +2 to +3. It increased. So once the oxidation number increases, then we say that compound or that atom or that species has been oxidized, because the oxidation number has increased. Because we've noted that the sulfate is just remaining the same. It's a spectator ion if you were to derive the ionic equation. Let's go to the hydrogen. In the hydrogen peroxide, +1, and we also have another hydrogen here, still having the same oxidation number, but when you come to this other side, hydrogen is still retaining the same oxidation number. So it is not being oxidized, nor is it being reduced. Let's go to the oxygen. Look at this. The oxygen in the hydrogen peroxide had an oxidation number of -1, and here the oxidation number went to -2. So if you recall, so look at this oxygen. We now have oxygen. Initially we had oxygen at -1, but it shifted after reaction. It went to -2. So if you recall your integers in mathematics, then you should note that -1 is greater than -2. So in short, the oxidation number has decreased. So once the oxidation number decreases, then we say that species has been reduced. So the species in our reaction here that was oxidized was iron, and the species that was reduced in our equation was oxygen. Maybe we can have